1. This is the structure for compound A. The oxidation state for the metal central is +3. In this structure, Cl and cyclopentadiene are negative charged ligands. Meanwhile, CO has neutral ligand. Next, number 2, this is the structure for compound B. The oxidation state for the metal central is +1. In this structure, metal central bind with triple bond has negative charged ligand and neutral ligand for trimethyl-phosphine. Number 3, this is the structure for C. The oxidation state for the metal central is +2. In this structure, metal central bind with triple bond and Cl has negative charged ligand. Meanwhile, ethylene diamine has neutral ligand.
For this question, we were asked to synthesize this trigonal bipyramidal platinum complex given the trans effect order. To synthesize the compound, we will use PTCl4, a square planar complex, as our starting material. Then, it will react with ethylene diamine, which will substitute the 2Cl ligand. This is the first step where a cis complex is formed. The second step, thiourea, which is abbreviated as TU, is added to form the trigonal bipyramidal intermediate. And this thiourea is at the equatorial position, which is trans to the ethylene diamine. If we refer to the trans effect order, thiourea should have substituted the ethylene diamine because the trans effect of thiourea is greater than NH3 or ethylene diamine. However, thiourea cannot substitute because ethylene diamine, which is a bidentate ligand, has formed chelating complex with the metal. This chelating complex is more stable and there is a strong force attraction between the metal and the ethylene diamine ligand. Hence, this is why the complex remain in trigonal bipyramidal geometry and not form the square planar complex.
Question 3, we need to choose the more stable complex from each pair of the complexes. So for A, it's between TiClCp2Cn and TiClCp2NH3Cl. Both complexes have 16 valence electron, which is stable for square planar complexes. To determine its stability, we consider the oxidation state of the metal center and the nature of the ligand. Titanium has the electron configurations of argon 3d2 4s2. In TiClCp2Cn, the oxidation state of titanium is +4. It can form an octet configuration. Meanwhile, in TiClCp2NH3Cl, the oxidation state of titanium is +3. This means it can leave a single d electron in the valence orbital. In addition, Cn is a strong field ligand which can take part in metal to ligand pi back bonding. This back bonding is a strong and give more stability to the complex. In conclusion, the TiClCp2Cn is more stable than TiClCp2NH3Cl. For B, it's between IRMe PME34 and IRCCPH PME34. Both complexes have the same valence electron which follow the 18 electron rules. These complexes also have the same oxidation state which are +1. So, other way to determine the stability is by looking for ligand that can form pi back bonding. IRCCPH PME34 is more stable because the penyl acetylene can form a strong bond with the metal via pi back bonding. So, in conclusion, the IRCCPH PME34 is more stable than IRME PME34.
For the question 4, which is calculate a effective atomic number for the complex 1, gold plus will give 70x electrons and 2 ethinyl will give 2 multiplied by 2 electrons and we get 4 electron here. When we total up the electron for this complex, we will get 82 electrons. So for the second complex, iridium 3 plus has 74 electrons and acetylacetonates have it's a bidentate ligand, so it have 2 donor atom. So 2 multiplied by 2 electron, it will give 4 electron from each acetylacetonate. So here we have 2 acetylacetonate, so 4 electron we multiply by 2 and we will get 8 electron here. And then phenylpridine is a bidentate ligand, so it have 2 donor atom from nitrogen and another 2 donor atom from the carbon. So here 2 multiplied by 2, we will get 4 electron here. So when we total up the electron for this complex, so the complex number 2, we will get 86 electron here.